Good morning, good afternoon, and good evening to all attendees from around the world. Thank you very much for attending our Saturday gathering. It is our 14th free Gemology webinars organized by AIGS. Thank you so much for your attending all the time. So I do believe today's webinar will be very interesting, useful, and practical for everyone. Today, our guest speaker will be Professor Lutz Nasdala. He has amazing academic background. He will give a topic on the applications of Raman spectroscopy in gemology. Professor Lutz Nasdala, he is a professor of mineralogy and spectroscopy at the University of Vienna, Austria. He got his doctorate degree in mineralogy, and after several postdoctoral appointments, he completed his habilitation in the. He completed his habilitation in He completed his habilitation in Johannes Gutenberg University in Germany, right? So because it's university for me, it's like very difficult to pronounce. I think it's Johannes Gutenberg University in Mainz, Germany. And he is very excellent because he's the one who got the Marie Curie Chair of Excellence in Mineralogy, which was the first ever Marie Curie in Chair of Excellence in Mineralogy. He also conducted and organized spectroscopy training courses in several countries, including Australia, Norway, and Thailand, Russia, Colombia also. His current research direction includes the defects and internal textures of mineral and gemstone analysis, and also the uses of gemstone as analytical references, accessory minerals, and radioactivity and radiation of damages of minerals. So he has a wide range of research. I hope you can enjoy tonight's webinar and try to learn as much as you can from Professor Lutz. So now I will give the floor to Professor Lutz. Hi, Professor Lutz, are you there?
Yes, I'm here, yeah.
Okay, how are you?
Yeah, thank you very much. Thank you for the friendly introduction, and yeah, thank you very much to everybody for joining on this unusual weekend day. Yeah, so let's see what we can do useful. Yeah.
Before you start, I want to ask you how should I pronounce the university? Johannes Gutenberg.
Yeah, I'm very sorry. It's when you just say University of Mainz, it will be fine. Johannes Gutenberg is the name. Yeah.
Oh, I see. It's quite a little bit difficult for me. Yeah.
Yeah,
but
sure.
Thank you so much. So I will give you the floor, give you the stage, so you can hope you enjoy your presentation.
Okay, so I will now share my.
Yeah, share your screen.
Share my screen, and yes, here we go. Okay. Before I start, I wish to say two things. First, in my personal opinion, this is a really great concept to handle the current corona situation and restrictions that we all have with such a weekly webinar series. And so I'm very, very happy to support this by giving a webinar today. The second comment is I wish to apologize in advance. In a test run, we noticed that between my computer and the satellite and your computer, there will be a delay of a fraction of a second, but some of the animations in PowerPoint may come with a certain delay. So I'm sorry if it should sometimes look a little bit fancy. I try to speak slowly and allow the animations to keep up. Let's see how much it will be hampered from connection problems. So this webinar is entitled Applications of Raman Spectroscopy in Gemology. And I do not want to make it a, let's say, a physical or material science seminar. It is really for people who use Raman spectroscopy as a tool that gives answers. So my plan will be mainly I will give you some examples for what you can do in studying gems, and I will give you a few examples for what could cause problems. And this will be preceded by some general remarks and a brief discussion of the physical background. So first, some general words. We deal with Raman spectroscopy, so I need to explain the terms. Spectroscopy in general is the study of the interaction of light or other electromagnetic radiation with matter. And Raman spectroscopy is the name of an analytical technique that is used to study vibrations of matter based on a special interaction of light or other electromagnetic radiation with matter that is called now Raman scattering. Here a note, the wording of Raman spectroscopy is a little bit controversial. It is common but not quite fully correct because we refer to the analysis technique. And well, spectroscopy as an analysis technique is obtaining qualitative information with the eye. So a spectroscope, I hope you can see it. Here, this is a spectroscope. Yeah, this is not what we use in doing Raman. So what we actually do, we use a meter, a device, computer connected, to obtain quantitative spectroscopic information. And for this reason, the technique maybe should be called spectrometry. But as I said, it's commonplace to call it spectroscopy in spite of we measure spectra and we use spectrometers. Okay, that's how it is. A Raman spectrum is just a simple plot of interaction intensity against the Raman shift. And the Raman shift is a wave number difference. It is the difference of the wave number of the laser used to excite the spectrum and the wave number of the scattered light, the Raman. So what is wave number? Very simple. Spectroscopists use wave number as main unit. It is defined as the reciprocal wavelength. So you can calculate the wave number by just dividing 10 million by the wavelengths in nanometers. So for example, 500 nanometers wavelengths correspond to a wave number of 20,000 centimeters minus 1. A few words about the wording, the terminology here. If you present your results, if you plot a Raman spectrum, then what you should plot on the x-axis is the Raman shift. As I said before, the Raman shift is a wave number difference. The unit is centimeters to the minus 1. You could also use wave number shift, or you could use relative wave number. This would be physically correct, but is less common. So Raman shift is the parameter to go with. What you should not use, what you must not use, is Raman frequency. The literature is full with spectra plotted against Raman frequency, but this is nonsense, this is wrong. Frequency is defined as a repetition rate, so frequency is expressed in hertz per second or multiples thereof. This is not what we deal with. We deal with wave number differences. Do not use wave numbers for the parameter. You don't plot intensities against something, you plot intensity. So a physical parameter shouldn't have a plural. You refer to the temperature outside and not the temperatures outside today. And even worse, don't use wave numbers for the unit as many people do. Use the correct centimeter to the minus 1. You would not say today we have 27 temperatures. No, we have 27 degrees. You would never confuse the parameter and its unit. So we should not do this for Raman spectra. We plot intensity against Raman shift expressed in centimeters minus 1. And there's another mistake, I'm sorry, but please never say Raman. The technique goes back to this person, Chandrasekhar Venkata Raman. It's not a French, it's an Indian physicist, and so the pronunciation is Raman, and Raman scattering, Raman spectroscopy. Maybe a few words about the history of the discovery of the Raman scattering and the early steps in the development of the technology. By the way, in the following pages, you may find little references on the bottom. You may look it up later on. These references support what I show in the slides, and so you may look it up and follow it up if you're interested. Raman scattering is an interaction that was not found by accident. It was actually first predicted as a result of theoretical considerations by Adolf Smekal in 1923. And it was in 1928 when Raman and Krishnan published the first paper in Nature, actually to be precise in March 1928. They published this paper about the inelastic scattering of light and liquids that they discovered. And already the second Raman spectroscopy paper, of course, at that time still called inelastic scattered, was published in June 28 by Landsberg and Mandelstam. So already the second paper dealt with a mineral, quartz, and before the paper was published, also calcite. There's a funny story behind these two articles. For about 60 years, so until the early 1990s, you will not find the name Raman spectroscopy in the Russian literature, because it was claimed that the discovery of the effect was simultaneously in India and in the Soviet Union. But as the Raman and Krishnan paper is cited by Landsberg and Mandelstam, it is quite clear who was first and who was second. But anyway, till about the early 1990s, you will only find combined scattering spectroscopy, KR spectroscopy, in the Russian literature. This is the reason. In 1929, Sir Chandrasekhar was knighted, and since he couldn't come to England, the ceremony was done in February 1930. And already in December 1930, Sir Raman was awarded the Nobel Prize in Physics. He was the first non-white person getting the Nobel Prize in Physics, and the second person at all. So, some years earlier, an Indian writer got the Nobel Prize for Literature. Anyway, there's another very interesting or funny story behind this. Raman was actually disappointed that he didn't get the Nobel Prize already in 1928 or 1929. And he was so convinced he would get it in 1930, he made travel arrangements already in July, even though the awardees are only announced in November. In 1948, he established the Raman Research Institute in Bangalore, India. Okay, so far about some generality and history, and now about the physical background of Raman spectroscopy. I will do it on a rather introductory and very simplified level. And actually, I will only comment on three aspects. The first one is the Raman scattering effect. I would like to explain the Raman scattering by comparing the infrared absorption, Rayleigh scattering, and Raman scattering using this very simple energy scheme. So on the bottom, we have a energetic ground state, and then the thinner line is the vibrationally excited state. Only these two energetic states are considered now. Well, it is possible to excite a vibration in a mineral or in a gemstone by letting absorb infrared light in the sample. And so only the light whose quantum energy covers exactly the energy difference between the two allowed energetic states will be absorbed, and then the sample vibrates. And all the other light quanta will just come back and not undergo any interaction. So from what is missing in the spectrum, we can conclude about the vibrations in the sample. This is the principle of infrared absorption spectroscopy, a very common technique also in studying gemstones. For example, type assignment of diamond and so on. Well, this interaction is not possible for visible light simply because the quantum energy of visible light is way too high for this interaction. So what will happen is we illuminate the sample with light and the very same light comes back elastically scattered. This is what we call Rayleigh scattering. Well, and very, very rarely we talk about 1 of 100,000 or even 1 of 1 million cases. It may happen that the incident light is not scattered back elastically, but a very small energy fraction is used to excite a vibration, and the big energetic rest is then inelastically scattered as a light quantum which has a little bit smaller energy. So I illuminate the sample with blue light and green light comes back and a vibration is excited. This is the basic principle of the Raman scattering, and of course through scattering the light loses a small fraction of its energy and is therefore shifted to lower energies in the electromagnetic spectrum. It is redshifted. There are 2 practical aspects that we should be aware of. The first one is the orientation dependence of the Raman scattering. I explain the orientation dependence by the simple example of a XO3 group. So for example, a borate group in a tourmaline or a carbonate group or whatever. The stretching vibration of this group are oriented along the bonds, as you can see it here. So very much simplifies, this group has stretching vibrations only in the east-west plane of your computer screen. So when the light comes from above, the laser light, then the polarization will be east-west, and of course an east-west polarized electric field of the incident light and possible east-west vibrations, there is a possible interaction. So yes, in this case we may see some Raman scattering. If the light comes from the sides and the polarization is north-south, then we have a problem because the energy that we put in is oriented north-south and the possible vibration is oriented east-west. So in this case, no interaction is possible. If the light comes from the side with east-west polarization, then of course we may see some interaction. So you can see that from the relation of the polarization of the laser light and the sample, we may see differences in the response. I show you 2 examples. The first one here, a pair of Raman spectra obtained from the very same zircon sample, but just under different orientation of the polarization plane of the incident laser light. And you can see you get the same fingerprint both times, but in the lower fingerprint, some lines, some important lines are simply missing. It's the same fingerprints, but the relative intensities may change appreciably. Why is this important? Well, we all use, well, not too expensive systems with rather cheap lasers, and the lasers that we use have a polarization of close to 99%. So you have to deal with polarized laser light unless you use something like a scrambler or other depolarizer. Here another example that shows how it is when you don't rotate the polarization plane, but when you rotate the sample under the beam. So for this barrel, you may see that some of the bands, like this one here, are fairly unaffected from crystal or sample orientation, and other bands may change appreciably. So the conclusion of this is the fingerprint pattern will be the same, but it may look different. And if you don't see what you expected to see, well, simply turn around the sample. This may change the picture or the spectral fingerprint that you get. So the third aspect of the physical background is how Raman spectroscopy is affected by photoluminescence. And I try to explain it again by a fairly simple energetic model. So I will compare Raman and Rayleigh and photoluminescence. Rayleigh scattering I elucidated before. We illuminate the sample with blue light comes back. We illuminate the sample with green light comes back. There is no interaction, there's no energy loss. Okay, Raman excites a vibrationally excited state with very low probability. So we illuminate the sample with blue light, green light comes back. We illuminate the sample with green light and red light comes back. Of course, this is not correct. When you illuminate the sample with green light, yellow light comes back, but I cannot use yellow in a PowerPoint presentation. You will not see anything. Okay. If we deal, or if we consider photoluminescence, this comes into the picture if we have an electronically excited level. Mostly or typically this would be an activator level within the forbidden band gap. And now this may happen. So you illuminate the sample with blue light, you excite an electron, and after a while, red light comes back. If you do the same with green incident light, now well then after a while, red light will come back. Yeah, why do I emphasize this? For this present situation of electronic levels in your sample, choosing green laser excitation may be very tricky because both the Raman scattered light and the photoluminescence emitted light have the same color. And in the spectrum, you cannot tell them apart. What you could do is just choose a different laser, because the very same sample studied with blue light, now the Raman scattered light is green, and the photoluminescence light, of course, is still red, because it does not really depend on the excitation, but it depends on the energy difference between electronic levels. Okay. To illustrate this, I have chosen just one example of a synthetic samarium 3+ doped zircon. This is the spectrum. The spectrum was obtained with green excitation. And so you have here an overlay of Raman and photoluminescence. But you cannot say just from looking at one spectrum which is which. By the way, let me add, it is a false friend to assume that Raman is always narrow and luminescence is always broad, as it is in this particular case. You will see other examples later on. But anyway, we can quickly show what is Raman and what is luminescence by doing the analysis with a different laser excitation. So with the argon 488 laser, the sample or the spectrum looks like this. And now we see certain signals do occur at the same Raman shift, so this must be Raman bands, and other signals are not seen in both spectra, so they are very probably luminescence bands or lines or emissions. Here to explain it, I have obtained full spectra, and I plot these full spectra on an absolute scale. So on the bottom here, the wave number scale, and to make it easier for you here on top, I have converted it to a wavelength scale. And you can see quite nicely in both cases, we have almost the same pattern of samarium emissions, one in the yellow, one in the orange, and one in the red range of the electromagnetic spectrum. In the blue excitation spectrum, the Raman pattern on the left is far away from the excitations, from the emissions, I'm sorry. And in the uppercase green excitation, there is a certain overlay, yeah, and we convert the scales now to Raman shift to relative wave number, and so we can see now the Raman patterns have the same Raman shifts, but one particular emission signal has an apparent Raman shift that is close to 2,200 here, but close to 4,000 here. So emissions will have different apparent Raman shifts. This is the way to tell them apart from the true Raman bands. And this is the explanation for why we see the differences due to emissions in our Raman spectra. So here again, the initial picture. So you have to repeat the analysis with another excitation. This will then help you. Now a few applications, and I need to add, of course, there's no claim for completeness. I just picked a few examples, and well, it doesn't really matter which device you have or you use, from rather simple spectrometer systems to advanced research grade systems. You will end up with a spectrum. And it is up to you what you do with the spectrum, either by experience or by using a database, a search software. You have to interpret the spectrum, you have to assign it to something in your sample. So you depend on software and databases in most cases. The first application, or the most simple application, is the identification of gemstones by, we call this fingerprinting. So we compare the fingerprint of Raman spectrum with certain references in the database. So here we have a fingerprint Raman spectrum, and by comparing with other candidates for yellow stones, yellow sapphire, yellow topaz, or yellow zircon, you can see very clearly that we have a really reasonable match with the reference spectrum of titanite. Yes, this is a titanite. You may see that the relative intensities in our spectrum and the relative intensities in the reference spectrum are a little bit different. This doesn't matter, different orientation probably, but the whole fingerprint matches quite well. An example for a white stone, so we obtain this spectrum, and by comparing with database spectra, we can easily say it's of course not a diamond, it's not a glass. Here we have cubic zirconia. Or for this example, here the match of the fingerprints tells us that we have colorless quartz. Well, the identification of a certain mineral species may, for example, help to tell apart different types of jade. I don't talk about replacements or fakes, I mean real jade. Is it nephritic or is it jadidic jade? And here in this case, we can say from the comparison with reference spectra, it's jadidic jade that we have in this specimen here. Of course, the identification by fingerprinting, so by comparing your fingerprint Raman spectrum with the spectra in your database, will only work out if you have the right match in your database. If you don't have your gemstone in your database, then the search software will give you the best hit as the answer. But you can see, well, only the highest intensity Raman band matches here, but the whole fingerprint does not match. So very obviously the answer is wrong. Now, this is not a borate here. We just don't have the right match in our database. Of course, if you have the right reference spectrum, then it's very easy to identify this gemstone as a diaspore. It's not always that you need to have the full fingerprint of the Raman spectrum. In some particular cases, it may be very useful to obtain the Raman bands in the hydroxyl stretching region at about 3,000 to 3,800 centimeters -1. So here we have two tourmaline crystals from the very same pegmatite in Madagascar, and from their different fingerprints again of OH vibrations, we can tell that they belong to two different mineral species of the tourmaline group. Beyond simple identification, we may also characterize the structural state of gemstones. Just a few examples for this. Here, Raman spectroscopy can tell us the degree of structural damage of the mineral zircon. So the lowest spectrum shows how the zircon looks like when it is crystalline, when it is very mildly radiation damaged. Gemologists would call it a high zircon. And with increasing radiation damage, so when you go up, then you see the Raman bands broaden. And finally, the upper spectrum shows a fully glassy, we call it metamict, fully radiation damaged zircon that only shows an amorphous or a glassy pattern, and the crystalline Raman bands are lost. So we can use this as a quantitative means to estimate radiation damage in zircon. Another example is this gem quality econite. And here also the Raman spectrum is, well, rather ugly. It's very broad. And this is the Raman spectrum of a glassy material, just to show how it would look like if it is crystalline. Here the very same sample after annealing and recrystallization. So Raman spectroscopy enabled us to say that this econite is indeed metamect. We can study inclusions, and the advantage of Raman spectroscopy is we can study these inclusions without exposing them to the sample surface. We can study inclusions in situ when they are still included, so which is very good for gems that don't need to be destroyed for analysis. Here we have a nice inclusion in a gem quality econite, and from the Raman spectrum we can quickly say that this inclusion is a K feldspar, here again compared to the host spectrum of the econite. By the way, the econite that you see on the upper right, I'll show you again, this is almost a textbook example for something metamict in the sense of Brögger's definition. Brögger defined metamict as a term for minerals that are amorphous but have crystal shapes. And here you can see we have a glassy material, and nevertheless the glass contains crystallographically oriented inclusions. So it used to be a crystal, and then it's self-bombarded with radioactivity unless it became a glass. Another example for an inclusion study here, a rough sapphire crystal from Sri Lanka, and the inclusion can be measured in situ, and here in this case we identified it as a spinel. Well, this can be interesting if you know of certain inclusions in spinels, sapphires from certain deposits. So the identification of certain inclusions may help you in telling about the environment of formation. Is it magmatic? Is it metamorphic? And maybe in some cases even allow some or support some provenance assignment. Of course, not always, but in some cases. You may identify synthetic stones. It's very similar to the identification of natural stones. You just compare a certain pattern, and then the fingerprint matches, in this case, with yttrium aluminum garnet. Another nowadays common synthetic material is the tourmaline. And here the Raman spectrum is still, I don't want to say ugly, but not very specific. We can identify this from the similarity with soda lime glass as a glass, but here Raman spectroscopy is not very well suitable. So Raman spectroscopy cannot distinguish among different types of glasses. To do so, we need to apply a different type of analysis. So, for example, some chemical analysis, and then we find out this material is a silicate glass doped with zinc and neodymium. And actually the neodymium gives us the chance to use the spectrometer not for Raman, but for photoluminescence. And so I have again plotted the wavelength scale on the upper x-axis to make it a little bit easier. You can see the neodymium doesn't emit any light in the visible range, but it has two emissions, one weak and one strong emission in the near infrared range. And from the fact that these two emissions are very broad, unstructured bands, we can conclude again that tourmaline is a glass. For comparison here, the emission spectrum of neodymium and the yttrium aluminum garnet, here you see a crystal field splitting of these two emissions into several individual stark lines. There is no such splitting, of course, in a tourmaline because there is no crystal field. This is a glass. Distinguishing synthetic stones from their natural counterparts, in contrast, is very, very challenging and only possible in a few cases. So Raman is completely unsuitable to tell apart synthetic diamond and natural diamond, or synthetic corundum and natural corundum. This is not possible. Other techniques such as photoluminescence, for example, would be much more useful here. This is one of the few positive examples. We can easily tell apart Tucholsky-grown spinel from natural spinel because of the non-stoichiometric composition of the Tucholsky spinel. The spectrum is very much broadened and therefore easily distinguishable from the spectrum of a natural spinel specimen. We can use Raman spectroscopy in identifying fakes. Of course, this is not always necessary. In many cases, you just see it's a fake. Here's a very nice example. When you see something like this, you know it's not an emerald. This must be a fake. Yeah, it's quartz covered with opticon. No analysis is needed to identify the fake. Or when you see something like this, yeah, this is not a blue sapphire. It's a colorless corundum, and the coloration comes from some filling of fractures with a cobalt lead glass. Okay, but in many other cases, we need some analysis to prove what is a fake and what is real. So for example, jewelry made of Bohemian garnet, we get a certain spectrum, and similarly looking jewelry, we get another spectrum. So only the lower specimen is really made of pyrope, whereas the other is a fake, cheap fake made of simple glass. Here we have the example of a fake turquoise. Well, first, it is easily recognized that this is not a turquoise because there is no match at all with the turquoise Raman spectrum. It's not a phosphate, what we have here. It's actually carbonate because a part of the spectrum matches very well with magnesite. So it's probably a porous gel magnesite that was used here, infiltrated with some color. And Raman even allows us to identify the dye. In this case, it is a so-called Astra blue, also identified from the simple fingerprint match of the Raman spectra. You can also try to unravel treatments, not always with Raman as the conclusive technique, but Raman may contribute to this. I will show you a few examples. Here we have a onyx specimen, and so it is a quartz, it is a chalcedony, but the question was, is the coloration natural or is it treated? The Raman spectrum gives us a pattern of fairly disordered graphitic carbon, so it is not a very well ordered graphite, it's strongly or fairly disordered graphitic carbon, but this alone is not enough information to tell apart natural origin or laboratory treatment. So this could be some graphitic carbon that originates from a natural hydrocarbon, but it could also be a graphitic carbon that is induced by, well, a sugar solution treated with acid. Yeah. So in this case, we need another technique to get a conclusive answer. In this case here, microscopy using photoluminescence microscopy. You can see on the right side that the dark band of the onyx is cross-cut by a hydrothermal quartz veinlet. So very probable in this case, the coloration is of natural origin. Another example for treatment is very common in gemology, the filling of emerald. Of course, it is a very important information for the trade what has been used to enhance clarity and coloration. Is it an epoxy? May it undergo some aging, or is it something that can be cleaned using acetone and refilled? In this case, the Raman spectrum consists of the patterns of beryl and Canada balsam. So this treatment is probably okay. Heat treatment of sapphire is a big issue. You know better than I know how much the market prices of untreated and treated corundum deviate. Well, one way of unraveling the heat treatment of corundum is to look for zircon inclusions. There's a specific decomposition reaction underwent by zircon only when it is in close proximity to corundum. Only close to corundum, the zircon will decompose and form a mixture of oxides. So here a picture from a study that we did a little more than 10 years ago. You can see a zircon chip and only the face of the zircon that was close to the alumina crucible is now overcrusted by a bedelliite, monoclinic zirconium oxide. And the same what happens here will also happen at the interface of a zircon inclusion in a gem sapphire. You can actually see this under the microscope. After heat treatment, the zircon inclusions will look like little snowballs because they are overcrusted by a bedelliite. Of course, the observation of little white inclusions is not conclusive enough to prove that there was some heat treatment, but we can analyze them in situ with spectroscopy. And actually, the spectral pattern here consists again of the Raman pattern of bedelliite, but also of the emission of erbium in the bedelliite. So this is another example for how we use Raman spectroscopy and luminescence spectroscopy to identify bedelliite and to show there must have been a high temperature treatment of this specimen. Another way to unravel heat treatment or to exclude heat treatment of sapphire is to study the Raman spectrum of the zircon inclusion itself. I commented a few minutes ago on the change of the Raman spectrum of zircon up in self-irradiation. So after several tens or hundreds of million years of self-irradiation, the Raman spectrum of the radiation damaged zircon will be broadened. If you put this in an oven, then of course the zircon will recrystallize and the Raman spectrum will be back to narrow. In conclusion, if zircon inclusions in sapphire give a broad Raman spectrum, we can positively exclude any heat treatment. So a sapphire that gives inclusion Raman spectrum of zircon that are broad cannot be heat treated. It's a positive proof that no high temperature heat treatment has been done. Okay, so a little range of examples for what we could do, what we can do. There are certainly more. And now I wish to comment on a few potential limitations and artifacts. Very simple. If you have a microscope attached to your Raman system, make sure that you focus on your stone. Here's a negative example. If you focus by accident, not on the stone, but on a fracture, then you will analyze everything that is in the fracture. In this case, it was supposed to be a garnet, but only a small fraction of the Raman bands in this spectrum are actually due to a manganese garnet. There are a few more Raman signals here that are due to silicon carbide, and no, there is no natural moissanite in this sample. Very probably we just deal with some of the polishing powder that was smashed into the fracture. And identifying the rest of the Raman bands was quite difficult, and finally we found a match in a pigment database. This is a blue dye used in a felt tip pen. And so we found out that the student who was supposed to do the analysis had marked the surface of the stone with a felt tip pen, wiped it away with acetone, and then we had the dye in the fracture. So make sure that you focus on the right place. Another perhaps even worse focusing mistake is this one. I usually finish my Raman courses here by giving students little gemstones with the task to identify the gemstone using Raman spectroscopy. And a few years back, one student came with this spectrum. Well, it was supposed to be a ruby, and this spectrum would perhaps match with this strontium sulfate mineral, so it was not the right hit. But again, only the highest intensity band matches, not the whole fingerprint matches, so something is wrong. And in a chemical database, we found this match. So not the gemstone, but the plastic box was analyzed. Yeah. So make sure that what you wish to analyze is in the focal spot area of your microscope. Another example, worn jewelry may look like this, and with a microscope system you will actually only analyze what is in the green little dots in the center. So at the moment we would probably analyze some body fat or fingerprint or yeah, something else. Make sure that you choose a good spot, a clean spot for the analysis of a few micrometers. Okay, this seems to look like a very good spot, but well, after the analysis, the very same spot looks like this. And so here we have a problem. Well, you should check the spot that has been analyzed after the analysis was finished. And if you see something like this, then very probably something is wrong. You may get a beautiful Raman spectrum like this one here. However, you don't know, is this the Raman spectrum of my mineral, of my gemstone, or is it the Raman spectrum of the burning product? And in this particular case, here we have an analytical artifact because it was a magnetite, and we found out by analyzing a different spot with only 5% of the laser energy, and you see we get the magnetite Raman spectrum. So the upper Raman spectrum is actually this of the alteration product in the laser spot. This leads to the problem of uncertain references. So here you can see we found matches of our, let me call it, burning product in some online databases. And you find all sorts of matches, which, however, cannot really be true. So there are some doubts that these references are really trustworthy. Yeah, I don't want to go deeper into this aspect. I just want to tell you, you need to be very careful. You need to be very critical. Quite a few entries in online databases, quite a few Raman spectra, even in peer-reviewed journals, may have some uncertainty, and so be critical. Now, and I take the liberty of showing you this sentence that was published in the last, or in the Raman issue of Elements. It appeared in April this year. Do not believe it just because it has been published. This is probably one of the take-home messages. Be critical. You may do better than others. Okay, another potential artifact is actually the introduction of external light sources. So here, a very nice example. This is supposed to be a synthetic corundum. The Raman spectrum, well, gives a match with some, oh God, coronane. This is a hydrocarbon. It can't be true. What is the explanation for this Raman spectrum? Well, the room light was on. If you take the same Raman spectrum with the room light switched off, then everything is fine. This is a problem that occurs especially if you use a green laser. There are green excitations in these neon lamps. So if you have your laboratory illuminated and don't protect the sample compartment from the room light, then you may end up with these additional parasite lights. So working in the dark may be advantages, at least with the green laser excitation. So now you see there's a perfect match with the reference spectrum of corundum, and everything is fine with the sample. Well, and of course, the probably most important and most disturbing problem and limitation is the occurrence of photoluminescence. So here, one example, how photoluminescence affects zircon when we use blue laser excitation. So 473 nanometers in this case. This is the Raman spectrum that we get. And if you now let the software search for a reference, the first hit is this one here, because the highest intensity of our spectrum is somewhere at 350 centimeters -1. But of course, this is not a reliable match. This gives us the wrong answer. Here we see the explanation. We have here the spectrum of dysprosium doped synthetic zircon with the same excitation. So what we see here is a combination of Raman and luminescence. To see the Raman spectrum alone, we just switch to another excitation wavelength, and red is a very good choice for zircon. There is no interference with any emission. And the interpretation is, in our spectrum, we see a combination of Raman and a lot of dysprosium emission. Similar problem, even worse perhaps, is when you try to study corundum with red laser excitation. So here the Raman spectrum is in close proximity to a mountain ridge that we call side bands. So we have combinations of the chromium R lines with vibrations in the sample. We can visualize these R lines by repeating the analysis with only 2% of the laser energy. And then you see the two R lines, and somewhere here, these side bands are very low in intensity. And this is all of the Raman that you see compared to this high intensity emission. So again, we have the choice, or we had the choice of the wrong laser. When you repeat the analysis with blue laser excitation, everything is fine and no interference with any photoluminescence. Same problem with chromium bearing topaz, imperial topaz, for example. So you get a spectrum that has no match in the Raman database simply because it is not a Raman spectrum. What we see here is the red emission of the chromium. And when we repeat the analysis with blue excitation, we get the nice Raman spectrum of topaz that allows identification of the stone. So whenever you have chromium in your sample, the red laser is not a good choice. It's like poisonous for Raman. But on the other hand, we can use the emission by identifying the stones, because in all crystals and all gemstones and all minerals, chromium sits in a different crystal lattice, and that's why it has a different fine structure of the emission. Provided we will have a reliable luminescence database, we may use this technique also to identify stones. So for example, very quickly, we can distinguish corundum and chrysoberyl, for example. Another example for Raman being obscured by luminescence is this one here. Here I don't have any picture because I only got the spectrum by email from colleagues in Bogota. They asked me, what is this spectrum? Of course, when you let the Raman spectral database give you an answer, then you will find some matches that are not really matches. So the best hit was brownite, which is a manganese silicate. No, this is not what we have here. What we have here is actually a xenotime. This is the spectrum of synthetic, non-doped, undoped yttrium phosphate, and you see only the right part of the spectrum, of the unknown spectrum, is that of the mineral, and the rest is an emission. So here we have the reference spectrum of yttrium phosphate doped with erbium 3+. So, and again, we can identify the inclusion by the typical Raman fingerprint of xenotime and by the emission fingerprint of erbium in xenotime. If we just have the right references, this can be supported, so in both cases. Another example for how we can use the photoluminescence is this inclusion in a gem corundum from Colombia. So this inclusion was extremely difficult to identify. With all lasers, we got a very poor quality Raman spectrum. But the PhD student found out that there is an emission of neodymium, and the fine structure, the fingerprint of the individual lines of this particular neodymium emission matches with that of allanite. So here again, we have the use of photoluminescence instead of Raman to identify an inclusion. So photoluminescence may be very difficult, may cause problems, but photoluminescence may also be quite useful in identifying. I wish to come to a few concluding remarks. So first, it is a very positive development during the last years that Raman spectroscopy is now really widely used. There are reasonably priced systems available. More and more laboratories use this technique in studying their specimens. This is a fairly positive development. photoluminescence is not seen anymore as the only enemy, the big problem, but more and more people turn into using photoluminescence as another positive tool in identifying stones, in gaining more spectroscopic information. Of course, this will strongly depend on the availability of databases. And this is something we all need to work on in the future to build up not only more reliable Raman, but also reliable photoluminescence databases. Well, I already mentioned one of the main take-home messages for you should be critical. As I said, a solid fraction of information, even in peer-reviewed articles and books, and of course in online sources, is tainted with uncertainty. And yeah, for a summary of Raman-related problems and artifacts, I have quoted 2 book chapters here that you may want to look up. But anyway, be critical, don't take the information as granted as true. Maybe you stumble over a wrong reference and then you repeat the mistake of others. Last conclusion is we do need much more training opportunities in the future. More and more people use Raman. Raman systems are fairly reasonably priced. Everything is fine. There are Raman systems everywhere. But where do you have the opportunity to learn it in a proper way? This is really a problem. There's a clear mismatch among or between the needs of the community and what is available. So we do need to strengthen the training, the teaching and training in spectroscopy, among others, to avoid uncertain and biased information in the literature. That's the end of my lecture. Thank you very much for your attention, and yeah, thank you.
Thank you so much, Professor Lutz. It's a very fantastic presentation. I do agree with your comments. Like, don't believe it because it's just published. Because when I was in the university, when I'm using the Raman spectroscopy to do the research in the aquamarine, I also feel like in different articles they give different reference. So that's really important for everyone. And also now I'm trying to share and launch the polling for everyone. So let's see what you have learned from this presentation. So we will give you maybe 2 or 3 minutes to do this polling, and don't worry about it, it's just anonymous. So let's see, if you have any questions, please put in the question and the answer Q&A session, so we will try to answer to you soon. And now I will try to review the questions a little bit. I do believe many of the attendees, they are from the universities or institutes or the laboratories. So I guess you have some technological problems to discuss with Professor Lutz. So please put your questions there. So we will try our best to answer to you. So we get a lot of good comments from the chat, Professor Lutz. They really
I appreciate this, yeah. Mm-hmm.
It's really interesting presentation and very useful and practical for them.
And I actually managed to stay in time.
Yeah, you really control the time very well. Thank you so much. So there is a question about is there a difference between a classic spectrometer and a Raman spectrometer?
A classic spectrometer and a Raman spectrometer?
Yeah.
I'm sorry, I'm not sure what a classic spectrometer would be.
Yeah, me too, I don't know.
So there are, of course, different types of Raman spectrometers that are used now. Most of them are dispersive, but we can also use a Fourier transform Raman spectrometer. But the actual design can be quite diverse. Yeah? So I showed you just a few pictures from simple devices to, not even in the picture, triple monochromators that are big systems. So there is no general answer. There are very different designs. And actually for gemology and for research, we have different designs of the optical paths, of the geometry. So there's no general answer to this rather general question. Sorry.
Okay, yeah, that's true. So now maybe we can go back to the polling session. So next, I will try to end the poll and share the results for everyone. So maybe Professor Lutz, you can explain to the attendees one by one.
Okay, okay. Yeah, I said this when you follow the old rule that Raman is narrow and luminescence is broad, then you may fail. So for example, in bedellite, the bands are quite broad, the Raman bands, and the Raman is much narrow, the emission is much narrower. So if we deal with rare earth elements, then we have actually quite narrow emissions, and Raman may be not that narrow. So it is not true. Of course, if it is very broad, it's more likely to be a luminescence signal, but you cannot just tell them apart from looking to the width. So when you remember, the Raman spectrum of titanite is much broader than the emission of dysprosium in a zircon, for example. Second question, Raman analysis can be done non-destructively. Yes, of course it can. Of course, it takes some experience. If you know that you have some highly light absorbing material, then decrease the laser intensity or choose a color of laser that is not so heavily absorbed. Yeah, it can be done non-destructively. This is actually one of the prime arguments for gemologists to use Raman spectroscopy. Third question, yes, the orientation does affect, so the answer false was right. The orientation of the gemstone does not affect the Raman fingerprint is a false statement. We do see, or we may see, appreciable differences, and so it may be a good hint or trick just to turn around the sample and redo the analysis for getting a different fingerprint. Yes, it is true, the very first published Raman spectrum of a mineral was recorded in the Soviet Union. It was Landsberg and Mandelstam who studied quartz, and they just didn't manage to publish their results before Raman and Krishnan. But yes, so in the Soviet Union, yeah. And Raman is an excellent method for telling apart natural and synthetic diamond. Not at all. This is a false statement. I said the Raman spectra look the same. You will need, for example, liquid nitrogen temperature photoluminescence when you want to know, is this a natural or a synthetic diamond? Okay.
Okay, so that's all the polling questions. So I will stop sharing. Let's go back to the Q&A. So there is one question. Can you explain how such a burnt spot can occur? Does it depend on the investigated material? I always thought Raman was a safe analyzation method.
It depends. If you have a transparent sample that does not absorb the light, then of course it is a non-destructive technique. But if you have something that is highly light absorbing, then the energy of the laser light will result in an increase of the temperature only on a micrometer scale. But as you saw, you may drill little holes. And in the case of magnetite, we talk about a spinel. There's a very high melting point, but in the presence of the air, the oxygen in the air, we actually oxidize this material. And when you look it up later on that page, there's a reference. People have studied this. So at even higher energy impact, you will form hematite, which is iron 3 oxide. So yes, it is impossible with a high power density to oxidize a spinel. It is not the absolute power. We use 10 milliwatts or so, but it is the power density. 10 milliwatts focused to 1 square micrometer gives us a huge power density. Yeah? And it's a common problem. So for example, if you have dark pigments or many substances are quite sensitive, and so sometimes it helps to just go to another excitation that is not so heavily absorbed, but sometimes you need to use the filter to weaken the beam.
Mm-hmm. Yeah, thank you for your answer. So one attendee, he's asking, any books on Raman spectroscopy of gems will you recommend?
Oh yeah, they are, well, I would actually recommend to start with the chapter that is on the second, but one last page of my presentation. Emanuel Fritsch and co-authors wrote a chapter on Raman spectroscopy applied in gemology in the Immunotes 2012 volume. This would be something to start with. Yeah. There are, of course, other review articles by Kiefert, by Henny. You can look it up on the internet. There is perhaps not really a textbook, but I would say there are quite a few very comprehensive review articles that can be used for beginners. Yeah.
Okay, so Professor Lutz, will it be convenient for you to send me the list of the documents they can refer to later?
Yeah, sure, yeah.
I will send the follow-up email to them tomorrow so they can see the list of the books they can refer to.
Okay, so I will just extract all the references from the presentation into one PDF document and send it to you. No problem at all, yeah.
Okay, thank you so much.
Mm-hmm.
So the next question. Is Raman peak position useful for quantifying the percentage of end members in a linear isomorphic series? For example, Galit or Jadet Cosmoco series?
I don't really, how can I say, I don't like the wording of the question. Is it? We cannot say so. It can be in some cases. Yeah. So for example, zircon and hafnium, when we replace the zirconium gradually by the hafnium, then we see a certain shift of the Raman bands and we can give some quantitative answer about the chemical composition. It is getting much more complicated when we do not have a simple single substitution, but if we have several substitutions. So for example, we have manganese and magnesium and iron 2 in a perovskitic garnet, then it's getting difficult. Or in jade, pyroxenes are like, I don't know, natural trash cans. They incorporate many elements, and every single element may have a course like a result in an upshift or a downshift, and we only see one spectrum. So first answer, yes, it may be possible. Second answer, it requires proper calibration by reference samples. And in some cases, we may be stuck in a situation that we have something like a system of 3 equations containing 6 unknowns. Then we don't have a solid, reliable answer. So sometimes yes, sometimes no.
Mm-hmm. Yeah, thank you for the answer. So the next question will be, did you have compared the results of basic Raman spectrometer, specially made for the table gemology and lab-grade instruments you use in mineralogy, and the terms of quality of spectrum for use in a database like RAF database?
Okay, yeah. So this is difficult now. Of course, I have the advantage that I have a research grade system available, which has a focal length of 80 centimeters. So for me, I have a much better spectral resolution. And if a sample has a narrow band, I see it as a narrow band. With a little box used for Raman fingerprinting of a gem, then of course, everything in the spectrum will be very much broadened. So something like quantifying the degree of damage will be much more difficult. And of course, the quality of spectra, well, what is the criterion of quality? If you say the quality criterion is the intensity of the Raman pattern compared to the intensity of the noise or the background, then actually these small systems do not do too bad because as a short focal length and with very few optical elements between sample and detector, you don't lose much intensity. So it always depends on the purpose, on why you do it. For fingerprinting, these small systems work very well, yeah.
Mm-hmm. Yeah, okay. Thank you for the answer. So one question is about, is penetration depth different for different lasers? If yes, how do we know about them?
Well, penetration depth is of course very different, not depending on the laser, but for example, mainly depending on the sample. So it's surprising to see that pyrite, which is an opaque mineral, is a fairly good Raman scatterer. So the light will only penetrate, I don't know how many atomic layers, but not too deep into the sample, and it's still enough interaction to see a fairly good Raman spectrum. Many labs use silicon as a reference sample. Light penetrates perhaps 2 or 3 microns into silicon. That's good enough. For many gemstones, you have a penetration far beyond the millimeter. And so this is not really the point you need to worry about in case of transparent stones. It's more important to choose an excitation that does not cause too much of light absorbance, because then you may heat the stone, you may even cause a burnt spot and so on.
Mm-hmm. Okay, thank you for the answer. So one more question, which I also want to know. Dr. Lutz Nasdala, would you please let us know what do you think about the main limits of the mobile Raman spectroscopy?
The main limits of mobile? I don't know. I mean, of course, these transportable systems are much smaller. They cannot be that big in terms of large geometry. So disadvantage, I would say, spectral resolution. If you want to have a high volume resolution, you need a microscope. And not only this, you need to have a confocal arrangement of the optical pathway. And all this, of course, needs some heavy equipment, let me say. So mobile systems, small systems may not have this. Of course, there's the possibility of using a portable or transportable system and operate it in combination with a glass fiber and a probe head. But still, so you will not have the full volume resolution, which of course may not be too relevant for gemstone analysis. So gemstone fingerprinting, it's fine. If you go for inclusion studies, then of course you need a big system and not just one of these small mobile systems.
Mm-hmm. Yeah, thank you. So there is a question from Dr. Ponswat. She's asking, as Raman can also be used to check surface diffused sapphire, could you please kindly help explain?
Yeah, of course, it could. Well, not only Raman, but also photoluminescence. So I don't know, if you diffuse some beryllium into the sapphire, then we may have an environment of the chromium that is not a corundum, but a chrysoberyl environment. And then we see is from a change in the emission. Of course, if you have a diffusion that leads to a reaction to the formation of a new phase, then you may see also the Raman pattern of the new phase. But here again, a general answer is not really possible. It may work in some cases and may not work in other cases. It's a matter of study and testing. Yeah.
Okay, thank you for that answer. So someone is asking if he wants to buy, which is the best spectroscope he should buy?
I will not give you any answer. This depends on your needs. This depends on your budget. And I actually would like to remain good friends with all the manufacturers. So I don't tell you in public what you should buy. Send me an email and we can discuss it.
Okay, thank you for your smart reply. So yeah, one more question is about, do we have a Raman database of all minerals found in the world? Where can we find them?
Yeah, this is a problem. This is really a problem, especially in the pigments, in the mineral pigment community. Every institute runs and maintains its own database. We have our own database. there are many Raman databases on the internet. Of course, the most prominent one is the RAF database. Well, it was established at the University of Arizona at Tucson, Arizona. Yeah, there they have only a green and a near-infrared laser. So if there are problems with luminescence, then there is no meaningful reference Raman spectrum in this database. And I don't want to go into too much detail. Let's say, look up their Galena spectrum, look up their Sepulite spectrum, and then you will know how much of reliability is in this database. It is undoubtedly the best tool on the market. So RRUFF, when you just look it up on the internet, this is the best thing you can find at the moment. But well, as the chief editor of a journal, I have to say, I often get papers where people use this as a Bible, and it is not the Bible. It is not the whole truth and nothing else. I don't know. I don't want to make any quantitative review, but a certain percentage of all entries in this database are affected by luminescence or have other problems. Yeah. So at the moment, we are doing better than compared to 10 years ago. We have good databases, RAF and others, but actually there's a strong motivation to have your own Gemstone database.
Mm-hmm. Yeah, thank you for the answer. It's true, we can refer to some database, but we cannot like take it as a Bible. So the next one is for the photoluminescence bands are always wide. Why photoluminescence bands are so wide?
They are not. This is not true. It depends on the type of transition. So some photoluminescence signals are really like a huge hump, and some of them are quite narrow. So when you recall the emission spectrum of certain rare earth elements, like when you recall the YAG, the yttrium aluminum garnet, there are narrow lines. They are not always broad lines. In other cases, we may have very broad bands. So actually, it depends on the electronic configuration. Or if we have a 4F element, a rare earth element, it is very narrow. If we have a 3D element, it may be narrow, like corundum in some minerals, and it may be broad, like corundum in other minerals, or manganese, it's always broad. It really depends on the type of transition and the electronic, let me call it band structure or level structure.
Yeah. So the next question is about, have you ever seen any Raman details on natural silicon carbide discovered about a decade ago in Israel?
Oh my God, yes. So there is a description of natural moissanite. For sure, we have silicon carbide in some meteorites, there's no doubt. It has been claimed that moissanite was also found in some terrestrial rocks. It really depends on how careful others are. Raman can tell you very quickly, this is silicon carbide, but you have to prove the natural origin. So, and of course, if there was some sample preparation that has involved silicon carbide polishing powder, then the whole study may be tainted with uncertainty. A very similar story you may know about the ultra high pressure diamond that was found in the world's oldest zircon a few years ago, and now we know it's just polishing debris. So Raman can tell you this is diamond, but it cannot tell you is it an ultra high pressure diamond or is it an abrasive, and the same is true for silicon carbide. Raman just gives you the answer, it's silicon carbide. You can even say which polymorph it is, but we cannot tell is it of natural origin or not. For this, you have to employ a different technique. So for example, TEM, if you can show that you have a certain intergrowth of the silicon carbide with the neighboring minerals, then it is likely natural. And because it will look different if you just have a smushed in polishing stuff.
Okay, yeah, thank you.
But
so,
to go back to this question, it's not impossible. Yeah.
Not impossible. Okay. So the next question is, what is the best choice for choosing the good excitation?
It depends on what you deal with. Yeah. So for several minerals, blue is not very suitable. So for example, remember dysprosium and zircon. For some minerals, red is not a good idea. Yeah, so if you have chromium, for some minerals, green is not a good idea. You may have erbium, or you may have uranyl groups or whatever. And even in the near infrared, you may stumble into neodymium. So there's no perfect answer. It really depends on what you mostly deal with. But I think the fact that many of the, let's say, reasonably priced simple systems are equipped with a green laser is first because a frequency doubled neodymium or diode laser is fairly stable and fairly cheap. And also it's a fairly good choice for many, at least, gemstones. But if you rely on a single excitation, you will sooner or later stumble over an example of a stone that gives you some problem. So if you have the budget, buy a Raman system with a choice of 2 or 3 lasers, or if you buy these small systems, buy a 532 and the 1064 or whatever to just be prepared just in case.
Okay, thank you for the answer, and thank you very much to Dr. Pongsma for sharing the address of the RAF website. So there is a question about the RAF. Is RAF a good general database?
You cannot ask me such a question in public. I already expressed that I am quite critical, and I see I often are confronted with published problems. Many people use it. It is a very good tool, but it is not perfect. So this is the politest way to express my opinion here. It is certainly a good idea if you find a match in the RAF database to look up an original reference that describes this particular gemstone to be sure. So obtaining an independent expert opinion may not harm.
Yeah. So talking about the database, someone asking is there any photoluminescence database that we can get access to?
This is even more difficult. I know of a luminescence database that is under construction at the CSIRO Clayton, so a part of Melbourne. There people have a combination of cathodoluminescence, but also photoluminescence spectra, and they work, and we actually contributed a little bit to this database. But in terms of minerals and gemstones, we are, I would say, still far from having a really comprehensive tool. The problem is, for photoluminescence, we need to have all the emission centers and all the different minerals. So we need dysprosium and zircon, dysprosium and monazite, and so on and so on. And then we need neodymium and zircon, neodymium and monazite, and so on and so on. And of course, this is quite challenging. It will be much less useful for 3D elements, so for transition metals. Of course, manganese emission of calcite and manganese emission in aragonite or another mineral are different. But as these signals are so broad, this is rather a rough tool for assigning them to certain phases. Yeah. So, but anyway, at the moment, people work on this, but I wouldn't know this is already available commercially. But actually, I don't know. I have to look it up. What the actual situation would be.
Mm-hmm. Okay, so there will maybe we choose 2 more questions to answer. So we will close the webinar. So the last 2 questions is there a formula to convert photoluminescence to Raman spectroscopy?
What do you mean? A formula to convert? I don't know what is meant with the question. But of course, you can predict by converting the wavelengths of a certain emission to the absolute wave number. So the red emission of ruby has an absolute wave number. And when you compare this with the absolute wave number of the laser, then you get a difference. And this will be the apparent Raman shift with this laser excitation that you are going to see. So if this is meant, yes, of course, you have to actually. If you know you have a certain green emission, then you can calculate where would it be in the Raman spectrum with my blue laser, or I better go to another laser. Yeah, we have to do it, and actually we can use this to not run into a biased interpretation of luminescence as Raman.
Yeah, thank you. I think that's his meaning, yes. So the last question is, how do you deal the different penetration depth of different lasers?
Oh, different lasers, yeah. For gemstones, for transparent gemstones, it's not too relevant actually, because what you analyze is a volume that has the shape of a truncated cone. So the light diverges into the sample, and the very tip of this truncated cone will be seen by the spectrometer with the highest intensity. It doesn't really matter how deep you illuminate your sample. So even if you do not have a confocal system, the uppermost range of the sample is what you mainly analyze. And of course, it depends from material to material, whether it is more transparent for the green or the blue or the red laser light. So this needs to be tested preferentially by obtaining an optical absorption spectrum, and then you know. But I don't think the answer is too relevant for more or less transparent stones.
Mm-hmm. Okay. So I plan to do this is the last question, but I feel there is a question very important to Alina. So he's asking the ruby intensity of R1 and R2 lies in laser-induced luminescence spectrum with chromium content above 100 ppmW could be quenched by iron 2+ ions. So however, this effect does not occur with chromium values below 100 ppmW. So did you study this effect? What is the physical meaning behind? Thank you. Yeah.
So I'm not an expert. I did not really study this myself. Of course, we know that iron 3+ does emit light in the red or the near infrared range. And we know that iron 2+ can quench very effectively other luminescences. But as to which degree iron 2 quenches, for example, chromium 3, it depends on the concentration. So I couldn't give an answer to this very specific question right now. I'm sorry. Mm-hmm. Send me an email and we can discuss it. Or actually, I would forward your email to a colleague who has studied more of chromium emission. Yeah.
Okay. So yeah, so tomorrow in the follow-up email, we will send your email to everyone. So if they have any questions, they can discuss with you a little bit. Yes. Mm-hmm. Okay, so thank you very much, Professor Lutz, for answering all these questions. It has been a very useful and practical presentation to everyone. Thanks again.
Okay, thank you very much. It was a great pleasure, and I am happy that I had the chance to contribute to this webinar series. Okay, thank you very much to everybody.
Thank you very much for the attendees. And so our next webinar will be in the July 18th. So the information will be on the website and YouTube channel. So we will send you a message later, so you can focus on our social media. So thanks again for your attending. Thank you so much, Professor Lutz. So bye-bye. See you next time.